In this work, we present a first-of-its-kind metric for measuring human performance in 3D object pointing and manipulation in virtual reality. The need to measure human movement and performance has increased exponentially with the recent spike in networking, mixed reality and robotic technologies. However, human movement in virtual reality and teleoperation is a complex phenomenon, particularly due to the complexities that arise in 3D space, especially when translational and rotational motions are combined. With the goal of understanding human perception, increasing situational awareness and the overall capability of proposing new concepts, methods and emerging technologies to maximize user immersion, a 3D metric to measure human performance is of necessity. A promising metric to measure human performance is Fitz's Human Predictive Model, short for Fitts Law. The law measures the required time to complete a set of tasks by quantifying the difficulty of the tasks based on their spatial settings, effectively combining time and spatial-based metrics under one formulation. The ability of the law to combine both is a promising step towards limiting the number of different types of metrics and rather focus on a single one that unifies these. Another benefit of using Fitt's law is the subsequent focus and popularity it has received from other researchers, increasing overall comparability between studies focusing on capturing human performance. Although Fitt's law constitutes a promising basis for conceiving a 3D metric, its simplicity and applicability and lower dimensions render it unsuitable for full 3D space without proper adjustments. More specifically, the original formulation by Fitts is limited to dimensionality, spatial arrangements, combining translational and rotational movements under one formulation, while finally, modeling the two most common types of human interactions, namely pointing and manipulation of objects. Consequently, the model suffers in numerous aspects when considering full 3D space. This is due to its suitability limited to lower dimensions in 1D and 2D, and solely for translational pointing tasks. In our approach, we make use of the simulation engine Unity 3D to render and accommodate the necessary physics, for us to conduct a study consisting of pointing and manipulation tasks of virtual objects, to study human motion. In terms of hardware, we make use of the Leap Motion Tracker for optical hand tracking and the virtual reality headset HTC Vive for stereoscopic vision. We recruited 20 participants to engage in our study, who completed 4 in total experiments with increasing spatial complexity. We studied the effects of purely translational tasks, with and without spatial arrangements in E1 and E2 respectively. In E3 we investigated purely rotational tasks, while in E4 we combined all of the above, rendering the last experiment a full 3D motion task. Furthermore, in each of these experiments, we investigate the two most widely used types of interaction, namely pointing and manipulation. The following clips represent the actual recordings of participants completing the virtual pointing and manipulation tasks. In our first experiment we were interested in approximating the simplest possible 3D motion by introducing tasks with forward translational motion. More specifically, we studied the effects of the size of the virtual cube, the virtual cube target and the distance between these two. In our second experiment we added directions as well as inclinations. We still maintained translational motion tasks. The addition of directional and inclination angles allowed us to investigate further whether motions around the user would introduce any significant changes in task difficulty. Contrary to the first two experiments, our third experiment studied the effects of purely rotational tasks. In these tasks, we were primarily interested in the effects of matching the rotations between the virtual cube and the cube target within a certain rotational tolerance. We also studied the effects of the size of the virtual cube and whether it would present any differences in timings. In our last experiment, we combined all spatial complexities from the previous 3 experiments. In particular, We study the combination of translational as well as rotational movements by varying all possible spatial information presented in higher dimensional space. Consequently, this experiment represented a full 3D movement task such as those seen in virtual reality and robotic teleoperation. Overall, we observed that while most of the extensions based on Fitz's law captured human motion well for E1 and E2, these struggled in E3 and most importantly in E4 where we combined all spatial variables. Moreover, our results showed that the most widely used models to date also presented significant low predictions when comparing pointing and manipulation types of interaction. Based on these results, the analysis and the implications of each spatial variable at each stage of the 4 experiments, we conceived our 3D metric based on Fitz's law. From our results, we show that our model can capture human motion in full 3D space, better than existing work even when presented with the most complex spatial settings. In conclusion, in this work we presented, to the best of our knowledge, a first-of-its-kind comparison between the most widely used model extensions on Fitz's law, and their applicability in increasingly more complex spatial settings. We observed that Fitz's law, despite its simplicity, proved to be a promising basis for the conception of our 3D metric. We moreover saw that our metric captured human motion better than existing metrics in the state-of-the-art, particularly when presented with the most complex spatial settings. From the experimental results, we support the combining translational and rotational movements is feasible via the use of Fitz's law, with the added benefit of also being able to capture the originally intended pointing tasks but also the manipulation of virtual objects. Thank you for your time and attention.